Okay, and now finally I'd like to welcome Jade Yu to talk about infinite mixture models.
Okay, so good morning and good afternoon, good evening for those who are not in the same time zone. So my name is Jade Yu and I'm a PhD student at the Department of Computer Science at University of Toronto. And today I will be presenting my work done together with my supervisor Yang Xu, titled Infinite Mixture Chaining, Efficient Temporal Construction of Word Meaning. So many words have been acquiring novel senses or meanings through time. So for example, this figure here shows the frequency change of the phrases to store food, to store electricity, and to store password in the past 2 centuries of English, taken from this Google Syntactic Ngram historical corpus, which suggests that this verb store is progressively taking emerging items or concepts as its novel noun arguments through time. So linguists have suggested that language change results from a functional need of maximizing the communicative expressivity under the minimum cognitive effort. So in this work, we follow this idea and propose a formal, efficiency-driven framework to explain the cognitive mechanism that underlies the flexible construction of novel word meanings through time. So one of the most influential views on word meaning extension is the theory of chaining that originates from research in cognitive linguistics and psychology. So this theory suggests that word meanings extend by linking new referents to existing denoted items when they are proximal in the semantic space, resulting in chain-like structures over time. So for example, after the emergence of passwords for electronic devices in the last century, people choose to use the phrase "to store my passwords" to denote this action of keeping this type of secret data, while rejecting alternative usages such as "to bury my passwords," which is largely due to the fact that passwords share more similar semantic features with those storable items compared to common noun arguments of another verb bury. So most existing studies on chaining has focused on 2 specific types of chaining mechanisms, both of which have taken inspirations from cognitive psychology research on human categorization. So one is the prototype model, which is illustrated by the lower left figure here, follows the prototype theory of categorization and assumes that each lexical category is represented by a single central prototype. And the exemplar model, as illustrated by the lower right figure here, takes inspiration from the exemplar theory of categorization, which assumes that each category is represented by a set of exemplars stored in our memory. Recent studies have developed computational models that implement the 2 types of chaining mechanisms to explain the historical extension of many semantic domains. Which of these models best describes the process of chaining remains as a debatable issue, although empirical evaluations suggest that the exemplar-based models tend to predict historical data better than the prototype counterparts. And moreover, all existing studies have assumed that the prototype and exemplar-based models together are adequate to capture word meaning extension or word meaning construction. Here we challenge this assumption and argue that chaining models should not only be evaluated in terms of their predictive accuracy, but should instead be assessed under the consideration called cognitive efficiency. And here we define cognitive efficiency as a trade-off between two competing constraints. One is the representational accuracy, which measures how accurate a model represents each members in a semantic category involved in the chaining process. The other one is the memory complexity, which measures the amount of information that a model needs to store in order to perform chaining. So under this view, prototype and exemplar models lie at the two extremes of the spectrum of chaining models. So at one extreme, the exemplar model offers a highly accurate representation of the mental state of our lexical category at the expense of a very high memory cost. While on the other hand, the prototype model pursues a minimal memory complexity by summarizing each category only using a single prototype, but at the necessary expense of a simplistic or sometimes oversimplistic representation, and therefore suffers from very low predictive accuracy. So in this work, we will present a theoretical framework from which we can derive a family of chaining models by varying a single parameter that modulates this accuracy complexity trade-off. So our framework draws inspiration from research in rational human and machine learning, which suggests that a conceptual category can be modeled as a flexible set of clusters of exemplars. And similar views have also been proposed in statistical machine learning, often in the tradition of the directly processed mixture modeling, which first assumes that there could be a potentially infinite number of clusters for each category, and then infer a finite set of non-empty clusters that optimize the trade-off between information loss and memory complexity. So for the scope of this study, we focus on the problem of predicting historical meaning extension of English verbs, where the meaning of a verb changes as it acquires new novel noun arguments through time, such as this case of the verb store. And specifically, we define a time-varying semantic category for each verb and syntactic relation pair, which consists of all of its attested noun arguments up to a time t of study, and which we call the support noun argument set. And we wish to predict which nouns could emerge as novel arguments for a verb under this syntactic relation R at time t, and we model this probability of association to be proportional to the overall semantic similarity between this novel noun and the support set of each candidate novel noun, of each candidate argument, and we're gonna call this novel argument, that is this NQ here, a query noun. Like for example, the password can be a query noun for this verb store. So to specify the semantic similarity function, we assume that each noun has a distributed meaning representation in a high-dimensional semantic space. We also assume that a support noun argument set can be represented by a set of cluster centroid embeddings inferred based on the internal semantic structure of each category. Like for example, one may infer a set of cluster centroids for a very polysemous verb, where each centroid could roughly represent the most prototypical usage of this verb under a particular sense. So following the psychological literature, we define semantic similarity as the mean negative exponential Euclidean distance between the query noun and the cluster centroids of a verb relational category. So to perform semantic chaining in a cognitively efficient way, we determine the exact number and locations of cluster centroids within each category by optimizing a trade-off between two cognitive constraints. The information loss term in the red box here quantifies how accurately a set of cluster centroids can represent the full set of support nouns. And the memory complexity term in the green box here measures the number of centroids a model has to memorize in order to compute semantic similarity during chaining. The relative weighting between the two constraints is controlled by a single parameter called lambda. And next we show how both existing and new models of chaining can be derived from this framework. In the case where lambda goes to 0, the model ignores the memory constraint and stores every support noun argument as a single cluster centroid in order to achieve zero information loss. While on the other extreme, when lambda goes to infinity or a sufficiently large value, the model is forced to pursue a minimal memory cost by storing only a single cluster centroid for each category, and therefore converges to the prototype model. And in the intermediate cases where lambda takes a small finite value, the inferred number of clusters will lie between 1 and the size of the support set. And we will call the resulting family of chaining models the infinite mixture chaining model, or InfMix. So to evaluate our framework, we collected a large dataset of historical noun-verb compositions derived from this Google syntactic n-gram English corpus from 1850 to 2000, that is the past 150 years or 15 decades. The table here shows some sample entries of data taken from our own dataset. Since word co-occurrence distributions are constantly changing, the semantic space needs to be updated to capture the information only up to the decade of study. So for this reason, we use the 300-dimensional hist-words pre-trained diachronic embeddings, where the embeddings for each noun at each decade t is based solely on its co-occurrence statistics from the current decade, while the future co-occurrences are not included. So during our evaluation at each decade t, we present the model with a set of ground truth novel arguments for each verb relation pair, together with a set of randomly sampled nouns that are never predicated by the same verb as negative alternatives. We then compute the percentage of cases where each chaining model favors the ground truth novel argument over the randomly sampled alternatives as a more appropriate argument. We tested a family of infinite mixture chaining models with different values of the trade-off parameter lambda, where both prototype and exemplar models can be considered as two extreme cases. We also include two simple baseline models to make predictions without any knowledge about semantic similarity. And so the two figures here shows the results of our evaluation. And we report the accuracy of an infinite mixture chaining model with lambda equals 0.24, since this model used the most well-defined or most coherent semantic clusters as measured by the standard silhouette score metric in the field of unsupervised machine learning. And we observed that in almost every decade of study, the infinite mixture model used near equivalent accuracy compared to the exemplar model and are superior to all other alternative models. And next we show how different infinite mixture chaining model balance the accuracy complexity trade-off. We measure the model complexity or memory cost as the average number of clusters inferred for every set of support noun arguments at each decade. And the left figure here is a recap of our theoretical projection of how different models will locate on the spectrum of efficiency trade-off. And the right figure here shows the empirically attested relation between memory cost and predictive accuracy when varying the trade-off parameter from 0 to a sufficiently large value. And as we can see, a wide range of infinite mixture chaining models, that is those right to the blue dot on the right figure, between the blue dot and the green dot, they can achieve almost equally good predictive accuracy compared to the full exemplar model, but with a much lower memory cost, suggesting that the infinite mixture model achieve a better balance between this trade-off between precision and accuracy. And we also interpret the semantic clusters inferred by the infinite mixture chaining model using the category of object nouns of the verb phrase to store as an example. The left figure is the 2D projection of the 4 clusters of semantically related noun arguments identified by our model in 1900s, and where the legend shows 3 most representative nouns within each cluster. And the right figure shows the cluster results for the same verb phrase in 1980s, where we found 3 new clusters that roughly corresponds to 3 newly emerged senses of the verb in the 20th century, such as this olive-colored cluster, which includes some biological related terms. And so to conclude, we present a unified framework of semantic chaining by taking inspirations from rational models of human and machine learning, and show both existing and new chaining models can be derived from this framework. And by varying a parameter that controls this cognitive efficiency between accuracy and complexity. We also show empirically that the infinite mixture model predicts these emergent novel noun-verb compositions equally well as the exemplar model, but at a much lower memory cost. Our result therefore suggests that word meanings are constructed over time in a cognitively efficient way. Okay, so that's everything for my talk. Thank you for listening, and if you have any question, please feel free to reach me out directly. Thanks.
So that was super interesting. I really enjoyed the talk. Thanks. I wanted to ask you about sort of an underlying assumption in this work, and I want to understand better your reasoning, which is it seems like you are taking, having different arguments as having different meanings, right? So verb has different, two different direct objects. Those are two polysemous meanings for the verb. And that's not the way I'm used to thinking about semantics. So I'm curious why you wanted to think about it that way, and for instance, how one might interpret this work if you think that meaning is more compositional and not this sort of like cluster-based idea that you had. Thanks.
Okay, thanks. Thank you for the question. Yeah, I think this is a very interesting question and very important question. Yeah, and I think I totally agree that the change of the syntactic arguments of the verb may sometimes not reflecting like the real underlying change of the semantic variation of the same verb or this same argument structure. Yeah, but I think here we are kind of like this is kind of like a very actually we are just like considering this way as a approximation, maybe a most straightforward approximation to approximate the meaning change of the underlying verb. Like for example, if we wanted to do this sort of diachronic predictions of verb meaning change, I think it's really hard to collect like some other types of data. Like for example, this word association data as mentioned by some previous speakers in this session, because we cannot like go back to the history and ask people from the past to evaluate like how this word associates with some other verbs like in the past. Yeah, so actually we are just kind of like taking this as a approximation, but I agree that this might not be the optimal choice to measure semantic variation. I hope this helps.
Hi there, we've got a question from Zoom, and I'll just ask the technical chair if they can read that.
Sure, yeah. So Babak Hamation Bourani is asking, great talk. Could this cluster-based method be used to derive more historically grounded embeddings for each word? Say, for example, a separate embedding for store in the 1850s compared to the embedding for store in the 1950s.
Okay, thanks. So maybe could you please like explain what do you mean by more historically grounded embeddings? Oh, you mean do you mean the historically grounded embeddings for individual words?
I'm guessing that's what the person asking the question means. Okay. So the way that the meaning has changed over time. Okay,
thanks. Yeah, thank you for the question. Yeah, I think that could be a very good suggestion, because in our work we are just using this kind of very established pre-trained word embeddings, which is actually derived from the same Google syntactic n-gram corpus we use in our study. Yeah, but I think, I agree with this view that maybe our method can help to improve this the quality of these word embeddings, because actually our model is kind of derived from a generative probabilistic model from machine learning, and I think maybe there could be some way to make use of this model to like better capture the semantic similarity or the variations between the different senses of a same verb across time. Yeah, I hope this helps.
If there's room for one more question. Okay, I'll ask you later.
Sorry. Thank you.
Thanks very much again to everyone for joining and to everyone on Zoom. Yeah, really enjoyed the session. So thanks.